Okay, at long last, we can finally start talking about something you can sink your teeth into and start to program with, and that's going to be the topic of Java streams. And I'll begin this discussion, this will go on for some number of days, with an understanding of the structure and functionality of Java streams at kind of an architectural level. We'll begin with an overview of the fundamentals of streams, and then we'll talk about the evolution of streams as well. So, first of all, what are streams and where do they come from? Well, they're a framework that provides for functional composition of processing behaviors that were first introduced into the Java class library in Java 8. And this came along in 2014. So you can see that it talks about what's new in JDK 8, which was quite a lot of new things. I won't go through them all right now, but the part that's highlighted here is there's a stream API to support functional style operations on streams of elements. And because they're always looking for ways to preserve the past and extend into the future, look left to shift right, or shift left, look right, something like that. They integrated streams with the collections framework, which allows you to do transformations of collections like hash maps or array lists or tree sets into streams where they're filtered and transformed and so on, and then you can convert them back into collections for other types of processing. A stream is a pipeline of aggregate operations that process a sequence of elements, sometimes referred to as values or data. Sometimes these elements are objects, but it's best to think of them as something other than a classic object, although sometimes they are classic objects. And as you can see here visually, you have input that goes into the first aggregate operation, which applies a behavior that provides output. That then goes as the input to the next aggregate operation, which then provides output, which goes into the next aggregate operation, which provides output, and so on and so forth. Aggregate operation is just a term used for something known as a higher order function. And a higher order function is just a function that applies a function. That's what a higher order function means, or returns a function. And in this context, these aggregate operations, and I'll show you examples in a minute, so it won't be totally abstract for long. An aggregate operation applies a behavior which itself is some type of function, and that behavior is applied often to every element in a stream. Not always every element in a stream, but oftentimes every element in a stream. And you can read more about higher order functions here. Don't let higher order functions, it sounds really ethereal and mysterious and highfalutin. It's just a function that takes a function as an argument, or returns a function as an argument. This concept of passing behaviors to aggregate operations is very important, because that allows us to modify the behavior of the program without changing its structure very much, which is a big win. If you can take something and keep it more or less the way it is, and then make some tweaks to it, you're often, not always, but often better off than if you have to rewrite everything again from scratch. There's a funny little meme here from the world of defense contracting, where you see the little dinghy here says original contract, and then you see the giant motorboat or yacht or whatever this thing is that says change order. So the idea there is if you do government contracting, you're always making your money with the change order. So you have the original contract, and everything that gets changed you have to modify, and that costs more money. So it's kind of a joke. But the point is, if you can parameterize things, it'll help to simplify coping with changing requirements. So you don't end up having to pay a lot more to do something that really shouldn't be that much more work. A stream is conceptually unbounded, kind of like a stream of air or something like that, which just kind of flows through the ethos. Though in practice, it's often bounded by practical constraints, because you often don't have an infinite number of elements in your array list, or an infinite number of elements in your hash map. You have a finite amount of those things. So practically speaking, it's bounded by certain constraints. I promised to talk about some patterns along the way. Well, here's the first pattern we're going to talk about. A Java stream is an implementation of the pipes and filters pattern from the classic book, Pattern-Oriented Software Architecture, Volume 1, A System of Patterns. I was co-author in a bunch of other books in this series, but not this one. But this is a good example of a pattern. It's called the pipes and filters pattern. You can read about that pattern here at this link at the bottom of the slide. And the intent of this pattern is to divide an app's tasks into multiple self-contained data processing steps, and then connect these steps together using intermediate data buffers to form a data processing pipeline. A good example of this pattern, which you may have used if you've programmed on Unix, is the Unix pipeline, which is also available, of course, on Mac and to some extent on Windows as well. So that's a good example where data flows through a series of filters that transform it. Same kind of idea. We're going to use this particular little example as a case study throughout some of the intro portions. And this particular example is available here in my GitHub repository in the Java 8 EX12 folder. And what it does is it takes a list of character names from the play Hamlet by Shakespeare, and it converts them into a stream using the of factory method. It then filters out any character whose name doesn't begin with a lowercase or uppercase h. Then we consistently capitalize things so that they start with a capital letter and then are followed by lowercase letters. Then we sort them so they're sorted in ascending order, and then we print the results out. So that's an example of a very simple stream that fits on a slide that I can talk about to illustrate some of the concepts we'll discuss. Streams has evolved a bit over time. And I'm not going to dwell on this particular topic because it doesn't make sense to talk about the evolution in detail till you know what it's evolving from. But I just want you to know that things have changed over time. The bulk of the streams framework came with Java 8, but then later versions of streams added support for new things. There's this thing called the T collector, which I think came into Java 12 perhaps, and this concept of take while and drop while, which were operations that were added with Java 9. And Java 9 also added this new API that implements the reactive stream specification. We talked about that briefly in our overview of how to program parallel applications with Java, and we'll talk about it a lot more later. So things have changed, but a lot of this stuff has been there for Java 8, which makes life easy. We'll talk a lot about reactive streams later in this course, especially in the context of Project Reactor. So that's the end of the quick overview of Java streams. Again, you don't know much at this point to program them other than seeing that one Shakespeare example, but we'll be getting deeper and deeper into the programming abstractions as we go through these lessons.